Hi, today we're going to look a little deeper on polar graphs. I hope you've had an opportunity to look at the Intro to Polar Graphs video so you kind of have an idea of the terminology and the language. But basically what we're learning to do today is we're learning to graph on a circular system. And so some of the things we've talked about in previous units are going to kind of all come back into play. So this is my new graphing system instead of the squares with the Cartesian coordinate. So at the center of my circular system is the point here in the center of the graph, which we call the pole. This axis right here that would normally line up with the positive x-axis is called the polar axis. We open counterclockwise this direction on the circle, and that's my directed angle. And then we have a directed distance. So when we graph on this directed distance, instead of making you draw bunches and bunches and bunches of circles, you'll be able to just take this line where your angle is and put a mark here for 1, 2, 3, 4, 5 as we plot. So the point that we're plotting right here is a polar coordinate, which looks like this. So it has a directed distance and then a directed angle. But when we plot these, it's generally, we plot the angle first, so we get the line where it needs to be, and then we plot the directed distance down. Just like we did in vectors, if we extend this line all the way to the other part of the circle, it's all on the same line, but we are reversing the direction. So where this point might be r, when we reverse the direction, the point down here would be negative r. So a little bit of that vector work on this as well. So as we're plotting here, we have the polar axis, directed distance. This is the angle we're talking about. This is the directed distance. And you'll see on your note sheet that you have some r, and then you can take theta and add 2n pi or subtract 2n pi, and we can take theta and we can add 2n plus 1 pi or subtract 2n plus 1. And it's okay to memorize this, but you know how I feel about that. I like to be able to do things that don't require memorization if we can fall back on something we already know. And because you already know how to plot angles and you know that angles can open in the positive direction or the negative direction, you got everything you need to know, and memorizing this is really not an issue. So what we're going to do in our notes today is we're going to work through being able to plot points and find multiple representations of a point. We're going to go through some conversion factors here, and we're going to convert from polar to rectangular, rectangular to polar, looking at just points, and then we're going to convert from rectangular to polar and polar to rectangular in equations. So that's the goal today, is being able to go back and forth between the two systems. So in the multiple representations, we'll start with the angle that we have, which is 2 pi over 3. So I'm going to go to my graph starting at the polar axis, opening counterclockwise. I'm going to draw the angle pi over 3, which is what this is right here. And then I'm going to do my directed distance down that ray from the pole, which is 2. So I'm going to start here and I'm going to count out 1, 2. And that's where my point is. And so what I'm going to do now is I'm going to try and figure out, knowing what I know about an angle, I can start here and have a coterminal angle that goes this way and stops there, or I can have a coterminal angle that goes this way and stops there. And that's going to give me more representations of the same angle. So the first one that I'm going to do here is I went from here to here and did my positive pi over 3 to plot the point. So now I'm going to go from here all the way back around this way to here, which would be negative 5 pi over 3, and still have the directed distance of 2. So this is one representation of the same point. And then to get the last one here, my scribble scrabble here, but we have, we're graphing, we were up here at 2, so we're going to reverse the direction to the other half of the line. And then we're going to do the same thing as we did before, and we're going to go in the positive direction to get the angle that goes with negative 2 down here, and then we're going to go in the positive direction to get to the angle here with the negative 2. And that's where negative 2, 4 pi over 3, and negative 2, 2 pi over 3 come from. Same thing here, we went positive to get to it, so then we went negative to get the second angle. We reversed the direction down here, and then we went in the negative direction and the positive direction to get to it. And so that's how we got multiple representations of 1, 2, 3 of the same point. So one more reminder, plot the angle, directed angle takes us there, using this point and the angle's positive direction and negative direction, reversing the direction and making sure that when I do the angles down here that I'm using the negative r. Sometimes students will get the r's and the negative r's confused, so just draw your picture and that should help you not make that common error. So as I always do when I'm working out problems for you guys, is I try to give you some narrative over here. So You can read through these notes or you can listen to the video where I'm explaining the notes. So don't worry too much about all the writing over here. Let's just focus on what we know. That we want to find, plot the point and find 3 additional polar points to represent the given polar coordinate from negative 2 pi to 2 pi. And so here's my point. So remember, the first thing you do is graph where the angle is and then count off the directed distance down there. So I'm starting at the polar axis and I'm going this way to negative 3 pi over 4, which is this piece right here. And then you can see I made 1, 2, 3 marks down the line. So instead of drawing circles, I'm just going to make my 3 marks, and here's that point. So remember that I went in the negative direction to get here. So now I'm going to start at the polar axis and go in the positive direction to get here, and that will be one representation, which would be positive 3, and if I go from here to here, 5 pi over 4. Then I'm going to reverse the direction down the line, so I go back to my pole, but now I'm going to do 1, 2, 3 in this direction, and so I'm going to have a negative 3 for my directed distance, and then I'm going to have the positive angle that goes from the polar axis to the line, and I'm going to have the negative angle that goes from the polar axis all the way back around here to the line. And so once I've done that, then the coordinates that I actually will find are 3, 5 pi over 4, negative 3 pi over 4, and negative 3, negative 7 pi over 4. Okay, so now I'm at 1b. So with this one is a little different because this direction, this is at the pole, right? There's no direction actually emanating out from either way. But I still have to think about if it were going out, going in the positive direction, negative direction on this side, and then reversing it and going in the positive and the negative direction on this side. So the only difference on this one is that directed distance is going to be 0 all the way down. So if it was 0 and I would normally have had a line that went through here, then I can go from here all the way around, which would be the negative 7 pi over 6. So the positive direction goes from here to this line, which gives me 5 pi over 6. So that's 1 point. And then imagine if I had reversed some value down this way, so I have some imaginary line right here, which we know isn't really there because it's at the pole, but that helps us reason through the angles. So then I'm going to go from the polar axis this way to where that line would be, and that gives me negative pi over 6. And I'm going to go from the polar axis around this way to where that line would be, and that gives me 11 pi over 6. So you can see the work was a lot less than all of that explanation on the last problem. All right, and 1c, let's do it one more time. So I'm going to go to negative pi over 2, which is going to be down here, and then I'm graphing 3 in the negative direction, which puts me up here. And so then again, I go in the positive direction, the negative direction, and I can get my 3 points. So hopefully that's kind of making sense, and we know how to make multiple representations of the same point. The next thing we're going to do is conversions, and so we're going to convert polar points to rectangular points and polar equations to rectangular equations and vice versa. And this is the group of information that I use. Well, this should look really familiar because this is very much like what we did in component form with directed angles. Remember, it was the pointy bracket r cosine theta, comma, r sine theta, pointy bracket. Well, we're just pulling these out and making them equations now. And when we go the other way, I need an angle and a directed distance. And since my rectangular coordinates, we plot the x and then we plot the y, I'm going to use tangent because that involves y and x. And so when I want the directed length, I'm going to use the circle equation to do that. So first, let's practice doing some conversion of points. Okay, so the process is kind of the same no matter which way you go. I want you to draw a picture. Sometimes if it's a quadrantal angle, you'll be able to convert it without needing any of those conversion facts because you're just going to know what it is. And then if you can't do it from just the graph, then you use the conversion facts. And so we're going to specifically be using x equals r cosine theta and y equals r sine theta. So the first thing we're going to do is sketch the point 2 pi. So we do the angle pi and then we go out 2. And so we can see right here where that is. Well, if you think about quadrantal angles, I would start at the origin, I would go out 2, to this point would be negative 2, and then I would stay put at 0. So from that picture, you probably should be able to go right here. And that's totally fine if you have the picture to support your work. If not, if I look at this and I go, I'm just not sure, then I go to my equations. So to find the x coordinate, the directed distance was 2. Remember, that's what this point means. And then I find cosine of pi. Well, cosine of pi is negative 1 times 2 gives me negative 2. And then I do it for my y. So the directed distance was 2. Remember, that comes from right here. and I do sine of pi, which is 0. 2 times 0 is 0. That gives me 0, and these two conversion facts are what is actually the coordinate point there. So that's how we do the points. When you can't tell from just looking at it, then you're definitely going to go to this step right here to do the calculation. All right, so the next one, the point was root 3 pi over 6. So I draw the angle pi over 6, and the directed distance down the line is root 3. Well, maybe I just don't recognize that, and it's not something that comes to me, so I go to my conversions. The directed distance from here is 3, and then I do directed distance cosine of pi over 6. Cosine of pi over 6 is root 3 over 2. Root 3 over 2 times root 3 over 1 is 3 over 2, because we would do root 3 times root 3, which is root 9. The square root of 9 is 3. And then we would do it for the y. So we have directed distance of root 3, sine of pi over 6. Sine of pi over 6 is 1/2 times root 3. So you get root 3 over 2, and this is your x coordinate, this is your y, and that's what it looks like. Pretty straightforward. So let's do the last one. And it's just in degrees instead of radians, so not any different. This is 45 degrees, and I would have 5 marks out on my angle because that's my directed distance. And then I do 5 times cosine 45, which is root 2 over 2, so you get 5 root 2 over 2. And then over here we get 5 sine 45, so we get root 2 over 2 times 5. So once again, we get 5 root 2 over 2. And that should make sense because this is a 45-degree angle, which means you have that special right triangle there, so the two sides should be the same. And so you can kind of reason through that. Now let's take it the other way. All right, so we're in a rectangular coordinate, so again we're going to draw the picture. So I plot the point -1, +1, and then my picture is going to be from the pole drawing a ray through that point that I just plotted on the rectangular system. So what I'm looking for now is the angle that is from the polar axis to R, and then I'm looking for the distance here. So to get this angle, we're going to use tan theta equals y over x because we have y's and x's. And then we're going to use the radius. To calculate the radius, we're going to use the circle. So if I'm calculating this to find my tangent, I know that y is 1 and x is -1. So that means I'm looking at tan theta equals -1. And we know that tangent can be negative in the first and fourth quadrant, but since I drew this picture to begin with, it should be very evident that I'm only looking for the one in the second quadrant because that's where my picture is. That's why drawing the picture is so important. And so then I know that that angle in that quadrant is 3 pi over 4 because that's what the angle in quadrant 2 that has a tangent value of -1. Then to find the directed length, so that's what we just found right here. Then I use my circle formula and I get -1 squared plus 1 squared, which gives me 2. And the square root of 2 is 2, and that's my directed distance. So the computation going the other way is not any harder. All right, so now let's look at 3b. And so it's 0, 2, so 0, 2. This is a quadrantal angle, so I should be able to look at the quadrantal angle and tell what it is. So I know when it's plotted right here, the distance from here to here is pi over 2, and I went 2 up to get to this point, so the directed distance is 2. Again, I could use that circle formula if I needed to find that if I didn't recognize that, but hopefully you saw that right away. All right, so now we're looking at 3c, so I have -5 and 5 root 3. So again, I plot the point, I draw the ray through the point, and so now I'm trying to determine the angle that goes from here to here and the distance from here to here. So when I'm doing this, I know tan of theta is y over x, so 5 root 3 over -3, and that simplifies to give me a tangent value, an angle that has a tangent value of -√3, which is a unit circle value. I know that it could be negative in quadrant 2 and 4, but we've drawn the picture in 2, so that's the only one I need to know. So that you should be able to come up with that to be 2 pi over 3. And so this is just kind of making sure you remember how we got that. All right, and then I use the circle formula to get the distance. So I do -5 squared, 5 root 3 squared, which gives me 25 and 75, which gives me 100 and a nice pretty square root of 10, and that's my directed distance. So you can see going back and forth with points, not a problem. Hopefully that was easy for you. Now let's tackle equations. So converting equations, same kind of similar is we're looking at what we have here. So if I have a radius of 2, radiuses deal with circles, And so we should recognize when you see r equals 2 that we're talking about a circle that has a center at 0, 0 and a radius of 2. And so that's what that means. So then when you're putting it into rectangular form, just think about that. The equation of the circle that we've been using to find distances is x squared plus y squared equals radius squared. So if the radius is 2, then the equation is 4. And this is one of those places students kind of make a mistake on, so pay attention to that so you're good to go. In 4b, we are given x equals pi over 3. So my pi over 3 angle is right here. I've drawn that picture, and I should know that pi over 3 is the same thing as 60 degrees, and that if this is 60 degrees, the side that's opposite is root 3, which leaves this to be 1 and 2. And so when I go to my equation, then I know that tangent of pi over 3 equals y over x. Tangent of pi over 3 is root 3. And remember, I'm not putting the values in here yet because I'm trying to make an equation, and I want an x and a y in my equation. So once I get my tangent value in, I can solve for y. So I'm going to multiply both sides by x, and I end up with this line, which is, it is a line, remember. I just tend to put the x in front because sometimes my x's slide up under that radical, and then all of a sudden I think I've got root 3x instead of root 3 times x. But you can put it behind, just be careful with that because this is just the constant, that's your slope, and then there's your x variable for that one. For 4c, we're dealing with secant, and unfortunately nothing that we've been working with has secant. We need to be in terms of sine and cosine, so I replace secant with 1 over cosine. Then I need to get it in a form I'm familiar with, right? My conversion fact is x equals r cosine theta, not a fraction with cosine in the bottom. So I multiply both sides by cosine, and I end up with r cosine theta equals 1. So remember, our conversion fact is x equals r cosine theta, and we have 1 equals r cosine theta, which means if this is equal to this, then 1 has to be equal x, and that is actually my equation. So last set, guys, we're going to go the other way. We're going to go from the rectangular equation to the polar. We're going to assume all our a values are greater than 0. So if I have this equation, this is the reverse of what I did a minute ago. This is a circle that has a radius of what? 3, right? You take the square root of that. So my equation, rectangular to polar, is just r equals 3. So when you see this, you know it's a circle. When you see this circle, you know this is what it looks like. All right. On 5b, we have y equals x, and so we're trying to figure out what that is. So here is my equation, y equals x, and so I know that to use that tangent, I need y over x, so I'm going to divide both sides by x to manipulate my equation, which is y over x equals 1. So what that means is I can replace the y over x in my conversion fact with 1, and then I need to know when is tan equal to 1, and that's going to be right here in the first quadrant. You could have worked it out this way by dividing both sides by r cosine theta, but I really feel like that's probably about the easiest way to go. And finally, 5c. So I end up with this equation. It has x's and y's in it, so I know I'm going to use this conversion fact because that's x equals and y equals. What I would do is I would kind of move that number over here and just rewrite my linear form so the 2 is out of the way. And then I know for x I can substitute r cosine theta, and for y I can substitute r sine theta. So I have 3 goes right here, and I make a substitution, r cosine theta, minus, and I make a substitution, r sine theta equals -2. So hopefully what you realize here is that think of this as kind of like a binomial. And so in that binomial, they both have a value of 3, well, both have a value of r, not 3. There's an r here and an r here. So I'm going to factor out that r because I'm trying to solve for r and I want 1r. And that leaves me with this once I take out the GCF. So then to get r by itself, I just have to divide both sides by what I have in my parentheses here. And that leaves me with something divided by itself, which is 1, so I get my r. And then -2 over 3 cosine theta minus sine theta on the bottom, and this is my polar equation. All right, so making sure you can go back and forth between points and equations is important. Next time we're going to look at the graphs of things. Thanks, guys.